I'll just use this mind map today. It will help us. Okay, so we have discussed about, our discussion today will be no more on insulators, no more on conductors. Now we are pure on semiconductors and semiconductors. So a bit of recap as that pulls you up. So if you look up at a semiconductor, and when we talk about semiconductor, now the two things in our mind are either silicon or germanium. So a semiconductor is supposed to have energy bands, and these energy bands are of two zones: valence band and conduction band. Anything that you find is not making sense to you, do not hesitate, please do ask me. And there is always an energy gap between these two, which is known as the energy gap or forbidden gap, and this is known as Eg. For semiconductors, this Eg is less than 3 electron volt. Okay, now if we look about an electron, now so temperature, right, fine. So at absolute temperature, that is 0 Kelvin, electrons will only be in the valence band. Is this also clear? Okay. Then further we say no electron can have energy in the range of the energy gap. If it has, it has to lose energy, right? And further we said, so if you are an electron, your energy can belong either to conduction band or it can belong to valence band. And if you are in conduction band, then you participate, this electron participates in heat and electric current conduction. Just make sure that you are okay with this mind map. And if you are in valence band, you only participate in bonding. That is, you are bound to the nucleus. Just check this if there is anything that you have not understood. Yeah, one more word we will write, that if you are in the conduction band, the electron moves freely and is not bound to nucleus. If you keep this, write this, draw this mind map and then follow the notes that I'm giving, they're more than enough. Here, electron is bound to nucleus. This is a pull out of last class. Okay? And further we said that in conductors, the energy gap is not there. Conductors have very minimal energy gap, or they have an overlapping. In insulators, the energy gap is very high, and in 3 electron volt, and in case of semiconductors, the energy gap is less than 3 electron volts. That means if you supply energy in the form of heat or light, the electron can be excited to move from valence band to conduction band. Shall we go ahead today? Okay. Now, so our discussion today would be on, semiconductors, and these semiconductors can be classified as intrinsic and extrinsic. Earlier days, this used to be a common question. Distinguish between intrinsic and extrinsic and give an example, and easily a 3-mark question used to come. Intrinsic and extrinsic. So we will be studying with intrinsic semiconductors. Okay. Sorry. So our study begins with intrinsic, and from here, please pay attention so that the notes become easy for you. Intrinsic semiconductors. These are semiconductors in their purest form. Semiconductors in their purest. And these semiconductors are either silicon or germanium. Okay? Semiconductors in their purest form. Now I'll draw the mind map, but I also will start explaining it to you so that you understand it properly. These are semiconductors in purest form. Both these semiconductors have got, I'll make star points, 4 valence electrons. That is 4 outermost electrons, which means 4 electrons in outermost shells, or outermost shell, the right word. Now, when you look into a crystal, 4 electron bonds with 4 electrons of neighboring atom. Have you understood this or not? See, I've got silicon or germanium, which is like a structure. So you have got a silicon atom. I have got 4 electrons in my outermost shell. This fellow has also got 4 electrons in the outermost shell. So these 4 electrons are going to bond with each other, and this bond will typically be your covalent bond. Clear? Sharing of bonds, covalent bond. Now, another thing that you should start realizing. Now, when they are forming bonds, when they are forming bonds, it is understood that the electrons are in valence band. Obviously, because in conduction band, whenever electron is in conduction band, they don't form bonds. The bonds will be formed when they are actually in a valence band. So again, the same thing comes at absolute zero. At absolute zero, okay, we will say, or extreme low temperature, or extreme low temperature, electrons remain in valence band, okay, bonded, which means no free electrons, and as such, semiconductor behaves as an insulator. Same thing you are studying, just getting a little bit deeper and deeper. Try to understand this. When you are a pure silicon or pure germanium, and I have kept you at, try to understand and then write it. I'll give you time to write, don't worry. Because if you write, you understand it. Okay. When you are pure a pure crystal of silicon or a pure crystal of germanium, then you have atoms with 4 electrons in their outermost shell. And then say this is atom 1. Atoms 1, 4 electron bonds with the neighboring electrons of another atom. And as such, all the electrons will be in their valence band, because you are seeing this at absolute zero, and they will be all in bonded state. And when you are in bonded state, none of the electron is free, which means that you don't have any free charge carriers, and that is one of the reasons that a semiconductor does not conduct at absolute zero. Because somebody might ask you 1-mark question, why does a intrinsic semiconductor or a pure semiconductor not conduct at absolute zero? At absolute zero, all the electrons are in the valence band and they are bonded with neighboring electrons of neighboring atoms. As such, the semiconductor will behave like an insulator. Is this much clear? Have you written it? Write it down so that when you read the book on your own or you read the notes, things become clearer to you. You are studying intrinsic semiconductor. You write, I keep on saying something, keep your ears open. Children, we are studying semiconductors now. Semiconductors are classified into two types, intrinsic and extrinsic. We are studying intrinsic semiconductors. What are intrinsic semiconductors? Semiconductors in their purest form, like silicon or germanium. And these semiconductors have 4 valence electrons or 4 outermost electrons in the outermost shell. And during the stage where it's at absolute zero, these 4 electrons bond with another 4 electrons of a neighboring atom, creating covalent bonds. And all the electrons are in valence bond. So they are bound to the nucleus and only participate in chemical bonding. And as such, do not leave any free electron, and thus the semiconductor will behave like a insulator and the semiconductor will not conduct. This is intrinsic semiconductor at absolute zero. Done? Shall we go ahead now? Now our story is what happens at room temperature. This was story at absolute zero, now at room temperature. Now at room temperature, electrons are freed from covalent bonds. यहाँ पे 2-3 नया चीज सीखेंगे हम. Electrons are freed from covalent bonds and thus create a vacancy. Now this is something that you have to understand and accept as a concept. I am an electron. I will not show you the bonding right now. It is bonded with somebody. And it is lying where, beta? It is lying in the valence band. Try to understand this, and you have to accept this analogy. This electron has been freed, right? This electron has been freed because you gave temperature. As such, this electron gets freed and it moves where? To the conduction band. Is this understood? It has moved to something which is known as the CB. And here it has created something which is known as vacancy. The concept को मानना होगा आपको. Electron has moved and has created one vacancy. Have you understood? This is, Arjun, clear? The electron has moved and it has created what is known as vacancy. So from vacancy we will write, whenever there is a vacancy, you have actually created what? Free electron has been created. If you draw and make it as a mind map, then it becomes easy for you to understand. ठीक है? That is what we will see now. So you have given, our job is like this. See, we are right now the electron is all in the valence band, right? And the electron is here, and this electron is somewhat, I say, it is somewhat bonded with another electron. Is this much understood to you? You have given energy, and after giving energy, what you have done, you have freed this electron. This electron has freed. You have made it free. And once you have made it free, the first thing that you need to understand is that जैसे ही free हुआ, इसने अपने original slot पे एक vacancy तो create कर दिया है. That is what I have written, and thus create a valency. All right, rather I should write creates a valency. Free electron has been created. Now, one of the easiest thing that we know as per an analogy is that it moves to conduction band. And participates, it moves to the conduction bands and participates directly in conduction. This is easy to understand. The trick is this part. The trick is the other part. Stays in valence band, stays in valence band, okay, and also participates in conduction. Now you might ask that in valence band, we have realized that in valence band, everybody undergoes for bonding. This is a unique feature of semiconductors, that if you supply energy, not at absolute zero, right now, do you understand what the scenario is? It is in room temperature, you have supplied energy. Once you have supplied energy and you have created a free electron, the free electron has sufficient energy now that it is not going back for bonding. Rather, it is free. It has created one vacancy and it is free, and it can still participate in conduction. So here we will write a note that this is, here we will write, this is a unique property of semiconductors in which electron of valence band also participates in conduction. Due to presence of broken bonds in the crystal. This is a unique property of semiconductors in which electrons of valence band also participate in conduction due to the presence of broken bonds. Children, if I would have reduced the temperature and brought it back to absolute zero, ये free electron जो है वो फिर जाके bond हो जाता था. हमें एक free electron चाहिए. Anytime you have a free electron, the free electron can always conduct. And in semiconductors, it does conduct. Have you written this much? Okay. The previous slide said what happens at absolute zero. The slide now is talking about what happens at room temperature. And you understood about a unique property of semiconductors in which electrons of the valence band, as long as they are free electrons created due to breaking of bonds, they also participate very nicely. Now, keeping this in mind, okay, no one is going to ask you detail about explaining these processes, but if you understand this, then the notes become easier for you to understand. Now, keeping this in mind, now apply electric field. So understand what is the scenario. You first took a semiconductor, you raised the temperature, excited it so much that it created a free electron in its valence band, and a vacancy is also there. At this moment, you are trying to apply an electric field. Why are you applying an electric field? You want to now tame this electron. Right? One is, if the electron has already gone to conduction band, no questions asked. It is conducting. If it is still in valence band, I need to make it conduct. So now you apply electric field to the semiconductor. Apply electric field to the semiconductor. To the semiconductor, assuming that there is at least one broken bond at some location try and understand this now. Understand and then write. Once you have freed an electron and you know that a vacancy exists, you are now, will you get it? You are now applying an electric field, assuming that there is one broken bond, and one complete bond in the neighboring zone. Possible? Very much possible. Is it getting difficult, or are you able to understand it? Sure, Arjun. Okay. So I have got a, yeah, please. Why not? Okay. So let's go back. We had a semiconductor in the previous slide and it was at absolute zero. So at absolute zero, the semiconductor behaves as an insulator. Why does it behave as an insulator? Because all the electrons, valence electrons, are bonded with the electrons of their neighboring, all covalent bonds. Then what did you do? You brought it into room temperature, means you gave temperature more than absolute zero. So if you give temperature more than absolute zero, electron gets freed. And if the electron has got freed, it creates a vacancy. That's what we wrote here. Now, once the electron has got freed, it has two choices. Because in a semiconductor, the energy gap is less than 3 electron volt. It can either excite and go to the conduction band. In this case, it starts conducting directly, or it can stay back into the valence band. Now, if it stays back in the valence band, it does not go and form a bond. It is free. It is with energy. So it participates in conduction. How? That is what we are going to see, right? And this is a unique property of semiconductors, that if you have a free electron in the valence band due to a rise in temperature, this is going to participate in electric current conduction because of the creation of a broken bond. So right now, my semiconductor is at a temperature which is at room temperature. There is a broken bond. There is a free electron in the valence band. At that condition, I have applied one electric field. What is an electric field going to do? An electric field is going to make the electron is a charged particle. So electric field's direction is the direction in which a positive charge moves. Electron is a negative charge, so it will move opposite to the electric field. That's the concept, okay? So we have applied an electric field assuming, see, if every electron was bonded, the electric field would not have done any job. If you apply an electric field to an insulator, suppose this is an insulator and you keep an electric field nearby, nothing is going to happen. But we are applying electric field now to this semiconductor because this semiconductor now is not an insulator. It has free electrons which might be either in the conduction band or maybe in the valence band. And while we apply the electric field, we assume that there is at least one broken bond and one complete bond in the neighboring zone. Possible? Possible. Now let's see what happens, okay? So we say electron, okay? As soon as you have, so electron from neighboring complete bond shifts to location of broken bond. Once this is done, a new vacancy is created, and on this side, a new bond gets filled. And this way, broken bonds get filled, but see, there is a change in the language. I'm saying this way broken bonds get filled and new and existing bonds are broken. No, I'll not use that word. I'll say in this way broken bonds get filled and new vacancies are created. Have you played Chinese checker? It is like that. One coin moves, one vacancy created. But new vacancies are created. Write this down, note it down, and ask yourself, have you understood what you have written?
What is the electron?
Electric field. It will make a movement and it will try to make a movement to the nearest, easiest slot. It moves and a pair electron says, come bond with me. Possible. Yeah, it keeps shifting. Somebody is shifting, some hole created. Somebody is shifting, some hole created. The idea is that there is a hole creation which is going on happening. Broken bonds means the earlier broken bonds. They get filled, but new vacancies keep on getting created. Okay, I'm just making one small drawing. Just try to understand this drawing. Electron moves. Okay, see this, electron moves. So rather than doing this, let me do it in this manner. Electron moves. As soon as electron has moved, hole created. You didn't see this. See this once again. Then only you'll understand. There is a vacancy out here. Have you understood? Okay, have an artist impression to understand it. Electron moves. What about the vacancy? Got filled. Where is the vacancy now? Here. Okay, same story now I'm saying in a different manner. Try to understand. Vacancy was here. Vacancy shifted. Are you understanding? If the electron moves, the vacancy is moving on this side. Clear? First vacancy was here. Electron moved here. So you generally see the moving guy. But in relativity, you should also see this guy has come here. Obviously, when you see a series of Christmas lamps and all, if this lamp is lit, then this lamp must have shut off. So we say that the shut off are coming this side. Our general tendency is to see illumination is progressing in this side. We will say shut off is progressing in this side. It's a relative concept. Arjun, have you understood this? Okay, right. Have you written this much? Understood? Because this is this point that we will be writing now. So we say the vacancy is shifted. Once again, children, if you have little bit of doubt also, first you studied about what happens at 0 Kelvin, everything in valence bond, and basically the story is that you are a insulator. Then greater than 0 Kelvin, what happened? You got a free electron and this created a vacancy. Free electron could have gone to conduction band or could have been in valence band. Then what did you do? You applied the electric field. Now once you applied electric field, the electron moves towards the vacancy, and in other ways the vacancy moves out here in this direction. This is the analogy. Okay. Now come. Now no more we will use vacancy, no more we will use broken bonds. We'll give a new term now. Broken bonds are analogous. Analogous means almost appears to be analogous to holes. Whole semiconductor and electronic study is all about electron hole combination. Holes. Can you give a charge to it then? Because your electron moves this side, the vacancy shifted this side. The vacancy is nothing but the broken bond, which you gave a better word called vacancy. Now you're giving it a better word called hole, and the hole has shifted this side. The hole is a positive charge. Conceptually, it's a positive. Imagine this electron went here, so must have created a positive charge. Was there a positive charge here before? No. Okay, let's say like this. I'm an electron, the vacancy is here. This place wants electron. So obviously this place can be considered as a positive charge. The electron moved here, neutralized. So that means it has created a hole here. Now this place is in hunger for one electron. So this is a positive charge. So don't you think actually the positive charge moves this side? Analogous. You have to understand in that way. It's analogous. Okay, so the vacancy is shifted. Broken bond is analogous to a hole. Is analogous, we'll write it, to a hole, and is assumed to be a positive charge. Assumed to be a positive charge. Children, whatever we are studying now is the study of intrinsic semiconductor, that is semiconductor in their purest form. Our main objective is, sir, why are you doing so many experiments with it? I want to check that is it going to be the slave that I want? Because I will be either giving it some temperature or some electric field. I can't do anything more. Does it have those properties which I want, in which I can make use of it? Those things we are trying to study. Okay. So electron moves in a direction away from electric field. Is there any difficulty in understanding this? No, because electric field is always designated how a positive charge would move. And here comes the interesting part, which in another way can be interpreted as a hole or a positive charge moving in the direction of the electric field. देखो, अगर इलेक्ट्रॉन इलेक्ट्रिक फील्ड से भाग रहा है तो होल कैसा जा रहा है? And this movement of holes is considered as movement of positive charge carriers. Okay, whenever we used to see a conductor, as you are writing this, in a conductor, the current flow is attributed only due to negative charge carriers, that is electrons. Whereas if you see electrolytes, liquids that conduct electricity, there I used to say in grade 10, they have got both DTDC and blue dart, because they have cations, they have anions also. The movement, the electric current in an electrolyte is attributed, the passage of electric current or the movement of electric current is due to both charges, positive charges as well as negative charges. Similar sort of things you are seeing out here also, that in a semiconductor, there can be electrons in the conduction band which can be responsible for current. There can also be holes which are actually moving in the direction of the electric field, and these holes are known as positive charges. Is this much understood? Now we're going to summarize all these things now. So let's put this into summary. So we say, and this is important, okay? This is the crux. So if you take an electric field okay, and you apply it to a semiconductor, and that is, it is happening in room temperature. Two things can happen. Number one, electron in conduction band starts moving opposite to applied electric field. The electron which is there in the conduction band, it starts moving opposite to the electric field. This constitutes what is known as IE, also known as electronic current. Is this understood? There is an electron which is there in the conduction band. How did it go in the conduction band? Because the semiconductor is exposed to temperature more than absolute zero. So some electron must be in the conduction band. If you are in the conduction band, you start to move opposite in the direction of electric field. And number two is holes in valence band which move along the electric field, and this will be known as your IH, which will be known as the hole current. Two type of movements. Electrons are moving opposite. This means I have two streams of current. And I say I, which is the current in the semiconductor, comprising of IE plus IH. The current in a semiconductor comprises of two streams. One is the electron current and one is the hole current. So if electron moves to conduction band, it leaves a hole in valence band. So for an intrinsic semiconductor, this is also important. For an intrinsic semiconductor, the number of holes, the number of electrons will always match the number of holes to n of I, where I is known as the intrinsic charge carriers, whatever it is. I is known as the intrinsic charge carrier. चलो एक बार फिर से देखते हैं. If you apply an electric field to a semiconductor, two things can be created. The electron in conduction band, if the electron is in the conduction band, then it will, how did it come into the conduction band? It jumped from the valence band. So it must have left a hole in the valence band and it has itself gone to the conduction band, but it will move opposite to the direction of the applied current and constitute what is known as the electron current. And the holes will move in the direction of the electric field and constitute what is known as the hole current. So you have two streams. One is a hole current, one is electron current, and both constitute what is known as the current in the semiconductor. And if an electron is free, that means one electron free means one hole also exists. So number of electrons will always be equal to number of holes, and that will be equal to I, which we know as the intrinsic charge carriers. Okay? I'm just reducing the size of this one because we need to write 2-3 more things on this slide before we go ahead. So electron hole pairs are continuously created. It's like replenishment. Mythology says whenever somebody dies, somebody must have taken birth in this universe. That's in mythology, says like that. It's something like this. If an electron has jumped, a hole has been created. So there's always an electron hole which is continuously being created. And now understand this thing. This electron jumped, created a hole. Where does this electron jump and go? Must have gone and occupied one more hole out there. So if you are having an electron hole pair are continuously created, and so are recombination of electron with holes. So what happens at equilibrium? There has to be some equilibrium. So at equilibrium we say rate of electron hole pair formation must be equal to rate of electron hole pair recombination. Try this. At equilibrium, electron pairs done. Anyone has not understood anything, just let me know. The story that is going is intrinsic semiconductors will not be useful for us. We will find that. क्योंकि यहाँ पे एक चीज हो रहा है. Whenever an electron hole pair gets created, again a recombination is also getting created. You want electricity to flow through it. So there should be continuous charge carriers which should be there. Which means that's equilibrium should not be there. The equilibrium should not be there. Okay. So let's go ahead. And now we see conductivity of intrinsic semiconductors with temperature. Nothing great and nothing new. You will hear the same thing, probably with some diagrams out now. So temperature increases. As soon as the temperature increases, more electrons are freed to occupy the conduction band. This is number one. More equal number. See, the first thing you have studied in the previous class also, but the second statement you are studying now. More equal number of holes are created in valence band. So due to increase in charge carriers, conductivity depends on temperature. A question which may come, somebody may ask you, why do you say that the conductivity of a semiconductor increases with temperature? More is the temperature, more number of electrons are freed to the conduction band, more number of holes are created in the valence band, and as such we see that due to increase in charge carriers, conductivity also increases. So let's make one small diagram out here which will make us understand this thing in a better manner. So let's make two bands, valence band. Let's make a conduction band. Okay. This is the energy of the conduction band. This is the energy of the valence band, EC, EV, and 1 minute. 1 minute. Okay. This is EV, EC. This much is my energy gap, EG, EV, sorry, EC, EV. Okay. This is the diagram for the temperature equal to 0 Kelvin. This is temperature greater than 0 Kelvin. Very easy diagram, children. Just see how it is. At 0 Kelvin, electrons are all, these are my electrons. The greens are electrons, okay? Let's say we have got 7 electrons out here. All the electrons are where? In the valence band. When you give it more than temperature, say 2 electrons, let's say 3 electrons have jumped to the conduction band. So out here we will have 1, 2, say 3, okay, and we will be left with 1 hole out here, 1 hole out here, 1 hole out here, and yeah. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, and let's make one more electron out here. These 3 electrons jumped and these 3 holes were created. That is for your illustration. Whereas, well, this is your electron and this is your hole. अब clear हो गया diagram से? So here, intrinsic semiconductor behaves as a insulator. You must have also heard about something very vague. We heard about superconductors. Certain materials behave as superconductors at extremely low temperature. That means if you are doing any operation with extremely low temperature, intrinsic semiconductor is not of my use, because an intrinsic semiconductor behaves like a insulator. Low on conductivity, so are not used for making semiconductor devices. This is of no use for us. If temperature is increased, conductivity increases exponentially. Why I went so much detail? I could have just made you write differences between, like in earlier we used to read, state the differences between intrinsic and extrinsic semiconductor. Question used to come like this: what is a semiconductor? Give an example. Distinguish between an intrinsic and extrinsic semiconductor. So you used to make a T format and write it. Full बच्चा चेप दो 5 mark 3 mark जो भी है. But now the questions come in assertion and reasoning or as 1 mark. They might hide. They will give you competency based questions. So your logic should be absolutely clear. What happens where? What happens to the whole current? Whole current always goes in the direction of the electric field. The conduction current, the electron current always goes opposite to the electric field. Hole pair recombination is same as hole pair creation. A hole is like a positive charge. And when you are at absolute zero, you are like an insulator and you are not used for making any semiconductor devices. That means we have to now look for something else, and that something else is known as extrinsic semiconductors. इसके बाद we will pick up speed. Don't worry about speed. If you understand, then PN junction understanding will be very easy for you. And we can see some application live practicals also. You can see. I can bring some semiconductors and show you. But if you actually light a candle near it, the bulb starts glowing. Fine. इसको पढ़ के नोट्स पढ़ लिया ना, आपका हो गया, यू आर मोर देन इनफ टू गो. And children, when you make your notes at home, colors bring life to everything. As much vibrant as you can making them lovely, colorful handouts, and use. I was liking the way he was using A4 sheets. I also use A4 sheets because whenever you want, you can perforate and put them in your folders. They're not in any book. You can take out few pages, staple them, read them, study them, keep them back. And from here, I told you to go to Google LM, and your same PDF, the notes that you prepare, if you have any scanner at home, scan them and push them on Google LM and ask Google LM. I'm saying him, it can be her also. So ask Google LM to prepare flashcards for you. 80 flashcards if you answer just sitting. Well, you can make your study interesting. Sit on a sofa. I always say, keep one dabba of namkeen with you, play your favorite cartoon or whatever you want, and just answer flashcards. आपका concept ऐसे ही clear हो जाएगा. Which one, beta? Exponentially. Exponentially मतलब समझते हो ना? Power function and exponential function. Like COVID was exponential. Exponential is 2 to the power x. Power function is x square, 2 square, 3 square. 2 to the power x means first day 2 to the power 2, second day 2 to the power 3, 2 to the power 4. ऐसे चला जाएगा. That's how. Okay, चले थोड़ा सा extrinsic semiconductors देख लेते हैं. Extrinsic semiconductors. Now we don't have an exact definition for extrinsic semiconductor, but to understand it, intrinsic semiconductors which have been made impure. Extrinsic semiconductors. Okay, for extrinsic semiconductors again, there should be some prelude. आखिर आपने इसको चुना क्यों? You can write the preludes. I can narrate them. Conductivity of semiconductors is low at room temperature. Conductivity of semiconductor is very low at room temperature. Okay. Conductivity can be increased drastically by increasing the temperature. Rather, we'll not write this. Okay. We'll keep it like this. Conductivity of semiconductors is low. We'll write like this. Conductivity of semiconductors can be improved drastically by addition of very low quantity of impurity. One atom per million atoms. इतना लो. To pure crystals of semiconductor. Did you understand now? Now, since the conductivity is very poor, what we are going to do is that he was actually a mama's boy. So he now needs to learn a little bit of college life. तो इसको मम्मी अच्छी छोड़े जैसा हो गया है ये. तो इसको भी क्या करेंगे? We will improve it drastically by addition of low quantity of impurity, 1 in million atoms, to pure semiconductors. So write down the definition. You can write down. I'll narrate it. Doping. D-O-P-I-N-G, doping. This question comes. Define doping. The deliberate addition of desirable impurity. The deliberate addition of desirable impurity. This is a deliberate addition. Deliberate addition of desired impurity to pure semiconductor to improve its conductivity is called doping. So it's an intentional task. Deliberate addition of conductivity, and we can add a word in controlled manner. Controlled manner means, what do you understand by controlled manner? Means very small quantity, that is like 1 atom per million atoms. It's called doping. So the impurity that you will add, impurity atoms, these will be known as dopants. Dopants. And the semiconductor plus dopant is known as a extrinsic semiconductor. Now you can correlate everything and answer for yourself. What is an extrinsic semiconductor? An extrinsic semiconductor is a pure semiconductor which has been deliberately doped. In bracket you can write, added with controlled addition of desired impurities in a very small fraction, 1 atom per million, to improve its conductivity property. Then that semiconductor is known as extrinsic. Intrinsic is like very pure, inert type. जैसा आपको मिलता है प्योर फॉर्म इज नोन एज इंट्रिंसिक. और इंट्रिंसिक के साथ प्रॉब्लम क्या है? इंट्रिंसिक्स do not conduct at room temperature properly, whereas extrinsics will conduct. So for that, how they will conduct, that also we will see. We will add impurity in a very controlled manner, and that impurity is known as dopant. Last, can I change the screen? Okay. So let us have a look at the dopant, and let us look at silicon or germanium. Okay. Now silicon or germanium, they are in 4th group. So we will bring the dopant from either from this side or from this side. So the dopant will come either from 3rd group or it will come from 5th group. Acha. 4th group means how many valence electron? 4 valence electron. Carbon and silicon are same. You studied. They are known as tetravalent. So this will be known as trivalent. Trivalent dopant or trivalent impurity. Boron, indium, aluminium. And these will be known as pentavalent. Pentavalent. Pentavalent में आएगा हमारा arsenic. Then we will get antimony. Then we will get phosphorus. These are pentavalent. Means trivalents have got 3 electron. They have got 5 electron. नेक्स्ट क्लास में जाएंगे. अगेन थोड़ा सा प्रेल्यूड देके छोड़ते हैं. पेंटावेलेंट इज ऑलवेज नोन एज डोनर impurity, and trivalent is known as acceptor impurity. Okay, we'll stop here, but it's a little bit of logic discussion if you're done with your writing. So, will we discuss conductor anymore? No. Will we discuss insulator anymore? No. Will we discuss intrinsic semiconductor anymore? No. We will discuss extrinsic semiconductor. What is an extrinsic semiconductor? An intrinsic semiconductor which has been added or doped with, doped means desired quantity addition of an impurity. The impurity can be trivalent or pentavalent to increase its conductivity. Now just see. Why is this fellow called donor? This fellow is coming with 5 electrons. And right now silicon is with how many electrons? 4. ये अपना 5 बच्चों में 4 बच्चा इसको दे देगा. Bond form कर लो. 1 electron will be excess. So once you add this, there is always excess of electrons. And one atom of is not going to come. There are many dopant atoms will come. Are you understanding? See, the semiconductor has free electrons. You just want to push a little bit more free electrons. The pizza came with a lot of spices, yet we gave you sachets so that you can increase the spice level more. So we are coming with donor impurity. Donor will come with 5 electrons. उसमें से 4 वो सिलिकॉन और जर्मेनियम को दे दिया, बच्चा चुप हो जाओ, एक extra. And this fellow is known as acceptor. What this fellow will do, he will come with 3. So he will pull what? 3 electrons from silicon and create 3 holes in them. So if you add this type of impurity, you create a semiconductor where electrons are majority charge carriers or negative charge. That what we'll study are known as N-type semiconductor. N stands for negative. और अगर ये ऐड करोगे तो क्या बन जाएगा? Holes are majority charge carriers. This will be known as P-type semiconductors. And after that, we will make a semiconductor. We will merge both N and P together, called the PN junction. And that will be our diode. Very stylish device. Works only in one direction. Up to a certain voltage, it will not act. Once you give little bit threshold voltage and above, it starts acting. Talk free. Reverse it, it doesn't work. Very stylish. You are feeding mobile's voltage to the mobile, battery's voltage plus the adapter voltage. But this voltage should not come this side, na? So there will be a unidirectional diode out here. ये सिर्फ एक जगह current जाएगा. If this fails, adapter takes over. We have the same thing in hospital. Cylinder, line connection. Patient is breathing. Cylinder empty, no problem. Then the line things comes up. How do we do that? We maintain 2 pressure difference. ये थोड़ा ज़्यादा pressure, ये थोड़ा ज़्यादा. Only one will be feeding. ठीक है? So next class we will be going and see what happens in an N-type. So your next question that comes is distinguish between N and P-type semiconductors. First question was distinguish between intrinsic and extrinsic. So intrinsic bye-bye. Now we will go for only extrinsic.